Let's continue our discussion about minimization of DFA. So if we say minimization of DFA, this is the act of minimizing our DFA from a large number of states to a minimum number of states. When we say minimal DFA, it means we have already reduced the DFA to its minimum number of states. Okay, to get the minimal DFA, we have two ways. We have equivalence theorem and Myhill-Nerode theorem or table filling method. But in this video lecture, we're going to focus on equivalence theorem. So let's start with the first step of equivalence theorem. Step 1, we determine if we have dead state or inaccessible state. We know what is a dead state. It is a trap state wherein when in a certain string goes to that state, okay, when we encounter additional strings or additional symbols, it will not go to another state. Okay, it's already been trapped. While inaccessible state, it means that it is not accessible by the initial state. Okay, so let's consider these two examples. So in this first automaton, Q2 is an example of a dead state, wherein if it encounters A after Q1, it will be trapped. All symbols will be trapped by Q2. Okay, so this is a trap state and dead state. And in this example of automaton, we have C, which is an accessible state, because S, which is the initial state, cannot access it. There is no flow, there is no path going to C from the initial state. Okay, as you can see, there is no input going to C, only leaving, only values leaving going to A or B. Okay, so this is an example of inaccessible state. If we have dead state and inaccessible state, remove it, okay, to get the minimized DFA. Okay, that's the step 1. So it means we already remove one state here. Here, another state. So we already somehow minimize our DFA by removing these two states. Okay, next, after removing that state and inaccessible state, let's proceed with step 2, which is creating the transition table. So in this example, we have three states. A is the initial state, B and C are the final state, where the initial state A, when it encounters a B input, it will just loop within itself. But in case we have A input, it will go to B state. In B state, if we have A, it will go to C state. But in case we have B input, it will just loop within itself. Same as with C, if it encounters B input, it will just loop within itself. And if we have A, it will go back to B. Okay, so this is the summary of the transition, or this is the transition table. So after creating this, we proceed with step 3. So we're going to group the non-final state to final state. Okay, so we're going to have two groups, one for final state and one for non-final state. That's step 3. So this will be the grouping. And this is called equivalence 0. Okay, the step 3 is called equivalence 0. We are separating the final state with the non-final state. So A is non-final, B, C are final state. So that's equivalence 0. Now let's proceed with step 4, wherein we're going to get equivalence 1. In equivalence 1, we're going to check if the behavior of the states within the group have the same output. If the output belongs to the same group. Okay, so for example, so we're just going to ignore A since we only have one state there. So we're going to consider B and C, this group. Okay, So let's check B. When we have A, it will go to C. So C is part of the group. So when A is encountered by B, it will just fall within the group of BC. Okay? How about B encounters B? So it will just live within itself. So it means within the group pa rin. How about C? C, okay, when it counters A, it will go to B state, wherein it is within the group, still within the group. While C encounters B, it will loop within C, which is part of this group. Therefore, B, C output after AB is still within the group state. Okay, so they are equivalent in P1. Okay, and then afterwards, you repeat this until you cannot detect any more, what do you call this? You cannot separate any more states. Okay, so that will be step 5. Repeat this until you cannot separate any state anymore. Then after you get that, you now proceed in creating the minimized automaton. So from here, it will be just like this. Okay, as you can see, BC is now grouped based on the grouping. Okay, so any values A and B will loop within B and C. And in case if it's A, if it's B in A, it just loop and then go to A. Go to BC if it encounters A. Okay, so that's the steps in minimizing of DFA using equivalence theorem.